All right, the first planet we're going to talk about is Mercury. I'm just going to do them in order. Some textbooks jump around. They don't do them in order. They kind of put them together because of properties. And it kind of makes sense, but I guess I'm kind of old school. I've always kind of just done them in order from the closest to the furthest out. So I'm going to give you some statistics here, not because I want you to memorize any of these numbers. You don't have to memorize the numbers, but they help us understand what makes that planet unique and what makes it special. So Mercury has a mass which is 0.055 times the mass of the Earth. And the circle with a cross in it means Earth, mass of the Earth. So it is about 5.5% of the Earth's mass. So a lot less massive than the Earth. Its diameter is 4,878 kilometers. You're like, what's that mean? That is about a third the size of the Earth. Yeah? This is only a little bit bigger than our moon. It's a little bit bigger than our moon. It's less than Mars, bigger than the moon. It fits in between those gaps there. It's about a third the size of the Earth in diameter. Now the density, this is very critical. The density is very high. In fact, it has the highest density of any planet. It's 5.43 grams per cubic centimeter, which means it's very dense material. Typical rock on the surface of the Earth is about 3 grams per cubic centimeter. Water is 1 gram per cubic centimeter. Okay? So 5 is really heavy stuff like iron and nickel, stuff that's really compact. That's what Mercury is mostly made of, especially inside its core. Its gravity, surface gravity, is 0.38 of Earth's gravity, which means if you were on Mercury, you would weigh about 40% of what you weigh here. So if you weighed 100 pounds here, you'd weigh 38 pounds on Mercury. And its rotation period, this is interesting, its rotation period is actually very slow. It rotates at 58.6 days. But it revolves, its revolution period, which is a year for Mercury, is 88 days. And it's actually 87.97 if you want to be picky. This is exactly 2/3 of that. And you're like, why would it be exactly 2/3? That's not by chance. Mercury's unique because it's so close to the Sun. Here's the Sun. Mercury also is an eccentric orbit, meaning it gets significantly closer and further away as it goes around in its orbit. When it's closest, it's 46 million miles from the Sun, but when it's furthest, it's 76. That's a big difference. So it has a highly eccentric orbit compared to the other ones. The eccentricity of its orbit is 0.206. Remember, 0 would be circular, so that's not very circular orbit. All right, so what happens is, because of that, the Sun influences Mercury as it goes around, and Mercury tries to make one side face the Sun all the time, but because of its eccentricity, it makes it so that it ends up being 2/3 of its orbit as it goes around. So what that means is for every 3 days on Mercury, there's 2 years on Mercury. I know, confusing if you lived on Mercury. The other thing that was interesting about Mercury is Mercury actually helped prove that Einstein's general theory of relativity was correct. Because in Newton's theory of relativity, here's the major axis of our ellipse, as Mercury goes around, it would just go around like that forever. Well, Einstein's general theory of relativity says, no, gravity actually isn't a force like Newton said. It's actually a warping of space, which acts like a force. But what that means is, and it's a subtle difference, but what it means is the major axis is going to precess. So it's still going to go elliptical, but the ellipse is going to keep changing. So what's going to happen is Mercury goes around like this. When it gets up to here, it changes slightly, so it kind of makes what we call a spirograph pattern. I don't know if you remember playing with spirographs when you were a kid, but the major axis is there, then it's there, then it's there, then it's there, And you see the major axis is precessing, it's rotating around. Well, after Einstein's general theory of relativity in 1915 predicted this, they went out, they measured the orbit of Mercury very accurately. Now, it took them many years, they couldn't do it back in that time. And they realized Einstein was exactly correct. In fact, Einstein was always correct. His theory of relativity was the most tested theory in all of the 1900s. Remember, it came in 1950, so that was a lot of years. All the way through now, and it is always passed. In fact, most people are like, we shouldn't call it the theory of relativity anymore.
Could you say it again, please?
Instead, we should call it the law of relativity. All right, so Mercury's orbit helped prove that Einstein was correct and his theory of relativity was accurate. All right. Let's talk about the interior of Mercury. Mercury, the interior here, has a large iron-nickel core. Iron and nickel. Iron is actually a very common element in the universe, which you'll understand if you ever take Astronomy 1303, where it comes from. We're not going to talk about that in that class. But iron is fairly common. Nickel too. These are heavy metals. Well, the heavy metals are all going to sink to the center. Remember when it was molten, they're going to sink to the center. But most of it became iron and nickel. And then you have this crust out here of more silicates and the kind of rocks like we have on Earth, especially like the moon. It very much is similar to the moon. Now, the interesting thing that happened with Mercury's core is because it was this big, large iron-nickel core, after it cooled off, it solidified. Well, when it solidified, it shrunk. Metal contracts as it cools, so the core got smaller over time. Well, that means that the crust had to fall in, so the crust fell in, but the crust was too big now, and so you got these folds in the surface. As the crust would fall in on itself, you would get these lines on the surface. We call these scarps. These are folds in the surface of Mercury. Actually, a scarp is a fold in the surface anywhere, but we see it predominantly on Mercury because its iron-nickel core was so large, and then it solidified, it cooled and shrunk in. Okay? All right, so let's look at some pictures of Mercury. This is a picture of Mercury here. Now, remember, Mercury from the Earth is always going to have one side facing. In fact, here is a globe of Mercury. We now have a globe of Mercury. And if you look at it closely, you see that it looks a whole lot like the moon. Full of impact craters all over the whole thing, all sides of it, okay? So it looks similar to the moon. When you look at the pictures here, you're like, oh, that looks similar to the moon. Well, let's talk about impact craters, because we're going to see these, and impact craters are found on all terrestrial planets, and most moons in the solar system too. So how do you form an impact crater? Well, obviously, you have an impact. So what happens is, right when Mercury was formed, it solidified and its crust became solid. But that would have been really nice and smooth. It's like when you take water and it's a liquid and then you let it freeze, it's going to be perfectly smooth, which is how they make sheets of ice for like ice skating and stuff like that. In fact, that's the whole idea behind the Zamboni that makes ice, is it chews up the ice in front of it and lays a whole nother layer of water down. Well, that water freezes and it's nice and perfectly smooth. So right after the ground solidifies, it was nice and smooth. Okay? Then you have an object like an impactor coming in. This is some large object. Doesn't even have to be super large. You can see there's all different sizes of impact craters, big, small, so on. And when it hits, it usually hits at a very, very high rate of speed. The reason for that, even if the rock's just floating out in space, Mercury's moving through its orbit very quickly and it'll hit it at tens of thousands of miles per hour. And if it's coming at another angle, it can hit it at even higher velocities. So when it hits, when the impactor hits, use this color here. When the impactor hits, the ground, it actually sends shock waves out through the ground. Essentially the sound spreading through, it's this wave, compression wave pushing through the ground. The impactor is usually destroyed. It is usually liquefied or even vaporized, depending on how much energy. Meaning it was a solid object, but all of a sudden that energy heats it up when it hits, and it becomes liquid and just flows into the ground, and you can't find it. So if there's a large impact, usually you don't even find the impactor. But what that does is all that energy coming through here starts to throw material outward from this hole that's created. And then all that material falls back down, and what you're left with is a profile that now looks like this. It actually comes up, then it goes down to the crater, then it comes up on the other side, and this was the original land. And so the impact crater, and you can also get rocks in the center here, now looks like this if you take a cut through it. We call this outer edge here, we call this part that sticks up higher, this is called the ejecta blanket. Where material, same thing on this side, where material that was in the hole got ejected outward. In here, this is called the central peak. And the central peak occurs because as it hits, some of the material, especially the liquefied material, will go straight up and come straight back down and land in the center and create this peak in there. And then the whole crater will be smaller, will be below the original ground level. Now, a couple of things to note here is that the size of the crater, the size here, is usually about 10 times the size of the impactor.